All right, these are the answers for the summer review practice exam. The app that I'm using allows 15 minutes of free recording. So this will probably mean that I'll have this summer review practice exam split into at least 2, possibly 3 short videos for you to watch and to understand. If you haven't already worked the exam, then turn this off and come back to it after you've made a significant attempt to get your problems worked out on your own. All right, let's take a look at the first couple of them. Number 1, which of the following metric relationships is incorrect? And number 2, put the 4 metric prefixes in the correct order from smallest to largest. All right, in both of these problems, we have to understand the relationship of the prefixes in the metric system. And so what order they go in and how many powers of 10 separate the 2 different entries, okay? So I pulled this off of a math and physics website that I like. You can get this anywhere. This is common knowledge. It's out there in the public domain. But when we look at this, what we want to look is the relationships between the prefixes. So in this particular arrangement that I'm showing you, the first column in the table tells us how many things there are in the prefix that's in the second column. So for example, if I look at kilo, there are 10 to the third things in a kilo of that thing. So 10 to the third grams in a kilogram, 10 to the third meters in a kilometer, etc., etc. In problem 2, we're going to look to see which is the smallest of the 4 possibilities listed. And when we look at those 4, we get nano. We've got a few other choices to pick from. So now we know we can refer back to this chart when we look at the question again. So now we can see that in fact there are 10 to the minus 6 liters in a microliter. There are 10 to the third milliliters in a liter, and there are 1 gram does equal 10 to the second centigrams, but what is not correct is 1 gram is equal to 10 to the third kilograms. In fact, it would be 10 to the minus third kilograms. So our answer for this one is B. Number 2, we want to put the 4 metric prefixes in the correct order from smallest to largest. And when we consult our chart of prefixes, we can see that our correct answer is A. Nano would be the smallest, followed by milli, and then centa, and then kilo. All right, number 3, 9.49 milliseconds contains how many nanoseconds? This is nothing more than a unit conversion problem. So we don't really have a unit conversion from milli to nano, but when we look on our chart, we can see that milli is 6 orders of magnitude above nano. So I have 10 to the minus third divided by 10 to the minus ninth, which you should get 10 to the 6th nanoseconds in a millisecond. Now I've got a conversion factor, so I can multiply 9.49 milliseconds times 10 to the 6 nanoseconds per millisecond, and that's going to give me 9.49 times 10 to the 6th nanoseconds. So our answer is B. On number 4, which of the following processes require a chemical change? Well, chemical changes require the breaking of bonds and or the creation of new bonds. And the only one where that happens is B, because in A, all we're doing is filtering or possibly precipitating out, somehow mechanically separating the water and the salt. In C, we can mechanically separate the nitrogen, oxygen, and other gases by doing a compression until they separate due to their boiling points, different boiling points. And on D, these are just different dyes that go into forming green ink, and we can again mechanically separate those through some chromatography method. So B is our only answer that makes sense. All right, number 5 asks us, which statement is consistent with Thomson and Millikan's work? with cathode rays and electrons. All right, you'll need to go back and consult your book or consult the web to find out what were Thompson's and Millikan's work. They didn't do it together. They did two different, their work, there's two different guys that did their work in separate years. But A is not true because cathode rays are just streams of electrons. So electrons from helium and electrons from hydrogen, they all weigh the same. So that can't be true. And since cathode rays are electrons, they're not going to be attracted to a negatively charged electric plate. They're going to be repelled by a negative plate. And D, the plum pudding model of the atom, is sort of the opposite of what's listed here. It's a uniform sphere of positive charges in which electrons are embedded like raisins in a pudding. So that makes C the only correct answer. 2000 is approximation. The number is really about 1,837. Number 6 asks us how many protons, neutrons, and electrons are present in the following ion, iron 56, 3+. Well, when we look at this, we know iron has 26 protons, and we get that information off the periodic table. And since the mass number is 56, the number of neutrons is the difference between those two numbers, so that must be 30. And since we know that the charge is 3+, it's got 3 less electrons than it does protons. So that must mean that our answer is A. Moving on to number 7, which of the following calculations is set up correctly to determine the volume in milliliters of aluminum? We're given the density, and when we say we're given that the sample of pure aluminum is 2.0 times 10 to the 24th atoms. Well, the first thing we're going to do is start with what we're given. So 2 times 10 to the 24th atoms. We convert this to moles by dividing by Avogadro's number. And then we multiply by the number of grams in a mole and then divide by the density to convert to milliliters. So when I do that, the only answer is D. Now notice in this problem, there are no units given. So it's up to you to write the units, to make sure that the units cancel each other, and then to recognize, okay, if I didn't have any units, how would this look? All right, going on to number 8. The mass spectrum of an element X is presented in the diagram to the right. Which of the following can be concluded, or which of the following is true? Well, if this is element X, it's a fair bet that it is a transition metal, but these peaks represent isotopes. They do not represent oxidation states. So A cannot be right. And furthermore, since these peaks are isotopes, they don't have any relationship to different electron sublevels. They're only an indication of the number of neutrons that are in the sample. And clearly, when we look at C, the atomic mass can't be 90 because we've got all these other peaks that aren't 90. So C cannot be right. That leaves us with D. You can see that the vast majority of the sample has a mass of 90, with other peaks at 91, 92, 94, and 96. So we can say with some confidence that our mass number lies between 90 and 92. You will be taught how to get to this number. But right now, all we can look at this qualitatively and say, well, my mass is going to lie probably between the two highest peaks. Number 9, you're asked to determine the perimeter of the cover of your textbook. You measure the length and the width, and how many sig figs should you report for the perimeter. Now, perimeter is just the sum of the lengths of the sides. So I've got 39.26, I've got 2 of those, and 24.83, 2 of those. And the question is not asking you what the number is. The question is asking you how many sig figs. Now, the rules for adding and subtracting significant figures is different, or they are different, than the rules for multiplication and division. Here we need to count the number of sig figs to the right of the decimal. The digits to the left of the decimal are not used to determine the number of decimal places in the final answer. All right, so we can see that when we do this, we've got two numbers to the right of the decimal. We add the numbers just like I would in the third grade, and I get an answer, and then I round the answer to the least number of places in the decimal portion, which is the number to the right of the decimal. For the least, the part of the problem has the least number of digits to the right of the decimal, and of course that's going to be 2 because they both are 2. Number 10. Oh, let me back up here on number 9. If this does not make sense to you, then you should do a Google search on significant figures for addition and multiplication, and another search for significant figures for multiplication and division, and compare what the rules are for doing this. All right, number 10. Based on the information shown in the table above, the empirical formula for compound Y is what? All right, here we're going to divide each element's mass by its atomic mass to get the number of moles, and then we're going to take the ratio of the number of moles. So in compound X, I've got 3 divided by 12, which is 0.25, and 0.25 for hydrogen divided by 1, which is also 0.25. So my number of moles of carbon and hydrogen are each 1, so my empirical formula becomes CH. So for compound Y, I have 6 divided by 12, or 1 half, and then 1 divided by 2. Sorry, not 1 divided by 2, but 1 divided by 1. We take the molar mass of atomic hydrogen, not the molar mass of hydrogen gas. So this would be 6 over 12, and that is a ratio with 1 over 1. And that gives me my ratio of 1 over 2. And so when I look at my choices, clearly my answer is B. All right, we're going to stop there. We'll do the second set of 10 in a separate video.